Okay, so first I would like to thank a lot the organizer for organizing this nice meeting. So a few days ago when we went to visit the temple, Carlos asked me why large deviation is useful, why should we care with large deviation. So it reminded me of a question I had few months ago. I mean, we had a visit by a lab in Paris called Gulliver. It's called Gulliver because they study things at all kinds of scale. And so the director of the lab asked me to make a seminar, but someone asked, why should Gulliver care about large deviation and rare events? And so what I answer then during the talk is related to very rare and extreme events. So in this case, probably you remember the story. I mean, Gulliver leaves, and then there is a storm, and suddenly it changes completely the world, and he arrives in Lilliput. So, I mean, this is one kind of rare events that have such a big impact that it matters. So some other kinds of rare events are less drastic and more and nicer.
Tes yeux rieurs qui se posent sur ma délicatesse. Sous tes ombrages, je n'ai à me perdre un moment. Tu étais tout ce que je suis tendre en dedans.
I mean, a very important point about rare events is that even when they are rare events always happen eventually. So maybe you wonder what is a rare event exactly in this case. Okay, so I mean, have you understood the meaning of the song itself? You know, the song, the title of the song is. Can you sing it again? It's Vienne l'amour. Can you translate it? No. At the coffee break, okay. Okay, so let me come back to my main subject. So we apply large deviation theory to climate dynamics, and it is also related to rare events. So there are these two kinds of rare events. So rare events with a huge impact, that's why we care about them. And I will talk about extreme heat waves and try to explain you how we use large deviation theory to study extreme heat waves. And the second kind of rare events is related to abrupt climate change. So more specifically, more scientifically, it will be the transition between two turbulent attractors. So just like in many other problems in physics or chemistry or natural science, you have two attractors, and if you wait long enough, you will see a transition from one attractor to another. So here we have the same kinds of problems in turbulent flows, and so we try to figure out whether the phenomenology is just like in condensed matter. I mean, whether we have transition rates, instantons, and so on and so forth. So I will have time probably to talk mostly about the first one, very briefly about the second one. So as an introduction, I give you a bit more about the motivation. So this is a picture about the 2000 heat waves over Western Europe. So this is the temperature anomaly, the difference between the temperature and the usual temperature. And so here the red color means that you have temperature difference of order of 10 degrees. So here the temperature is averaged during 2 months. So 10 degrees up during 2 months is very large. And probably you remember that there was a huge impact then. I mean, people say that 70,000 people were dying on top of the usual number during this 2 months. And here you see in Paris, this is in Paris, and it is you cannot read it probably, but it is written that if you have lost one of your relatives, you can call a special number to find him. So it was a huge stress on the society because mostly because of the unpreparedness of the government for these kinds of events. So the basic question here is what is the probability of this event? Or rather, we will talk about the return time. So people want to address the question, when will we have the next such an heat waves? What is the return time for these heat waves if we are in the current climate or if we are in a changing climate? How these return times will change? And so this is the question we want to address. So there are many issues about it. So when you look at the current literature, you can find any numbers. People will tell you that the return time of such an event in the pre-industrial climate was 500 years. Others will say 10,000 years. So it just means that we don't know. I mean, you see that the numbers, several hundreds of years, is too long to do something meaningful based on the historical records. So the only thing we can use are models, and models are the best tools we can use, but there are many problems with them. So I will try to explain you why large deviation may be useful to study this. So here, as I told, the scientific questions are what is the probability, return times, and what is the dynamics that leads to these rare events? So can the dynamics may be predictable in the sense may we have some instantons that describe the dynamics that leads to the events? So the event itself will occur through a Poisson process. So when it occurs is random, but how it occurs may not be random. And so my main point here will be how to sample those rare events. The problem is that we have a model which is very complex. And so a direct numerical simulation is not a reasonable approach because we want a model that is as precise as possible, so it will be extremely complex by construction, but then it will be so complex that it will be extremely hard to sample it. And so that's where I want to use large deviation theory, to use a rare event algorithm based on large deviation theory to sample the models and basically to give a much better answer with these tools. So as an illustration of the second kind of rare events, I mean abrupt transition, let me show you the examples of Jupiter's zonal jets. So Jupiter is a gas planet, and so you can see these colors here. They are correlated to the vorticity of the flow. And so you see that when the velocity increases with latitude, we have one color. When the velocity decreases, you have another one. So this banded structure is related to very strong jets. And so you can see them actually here on this set of picture that makes a movie. So it's a genuine turbulent flow. We have Reynolds numbers of order of 10 to the 13, and numbers of degrees of freedom of order of 10 to the 50 or something like that. So it's huge. It's way up the Avogadro number. Still, it's organized, forming these jets. And so you see the velocity profile here for this jet. So this is velocity on this axis and latitude on that axis. So you see you have dozens of jets to be compared to one jet per hemisphere on the Earth. And the main point of this picture is the comparison between the red curve and the black one. So one comes from Voyager data and another one from Cassini data. And in between the two spacecraft, there have been 25 years. So within 25 years, nothing has changed. You see the two curves are nearly the same, except for very small change here and there. So the system is extremely stable for a very long time, although it has this very turbulent flow and this self-organization. Although it has not always been like that, and something drastic happened during the period 1949-1940. So then suddenly, the observers have seen the appearance of these three white ovals, which are giant anticyclones. And basically what happened is that one of these jets became unstable. And so suddenly, the system changed completely its attractor, and you had a switch from one attractor to another. So what I want to argue is just like a phase transition, a non-equilibrium phase transition, a situation of bistability for which you have two attractors, very stable ones, and from time to time you have a random shift from one attractor to another. So here too, the problem will be dealt with large deviation theory for the same, because it is a large deviation problem to study this random transition. So I won't explain you what is large deviation theory, but I think all of you may understand why this may be useful for these kinds of problems. Okay, so let me begin with the extreme heat waves problem. So what is it about? So this is what you find in the classical literature. So this one is about the 2010 heat waves over Russia. Maybe remember there were fire all over the place. And so the point is, so what people use, you use a model, basically the weather model, which are adapted to climate. And one field which is very interesting is the 500 hectopascal geopotential height. So to simplify, you can think of it as being the pressure in the middle of the troposphere. And so those lines are isopressure lines. And so you see that here, it curls this way. Here you will have an anticyclone. And correlated to this anticyclone, you have, when you look at the sea surface temperature, you have a very hot area. So this is basics meteorology. When you have an anticyclone, it's hotter, and when you have cyclone, it's cooler. And so the point is that the dynamics, when you look at on the larger scale, which is better to understand. So this is the speed on the top of the troposphere at about 10 kilometer height. This is a movie by NASA. And so you see here there is a strong jet. You see the speed is localized nearly this very narrow bands. And so this jet is around the planet. It is a coherent structure that is always there. Sometimes it is a bit more feeble, it disappears a bit, but the coherent structure itself is always there. It is related to a strong temperature gradient between polar parts and the southern part. And those flows are dominated by the Coriolis force and this pressure gradient. And so when you look at the dynamics of this jet, it has been understood since the 40s that you have something called baroclinic instability and Rossby waves. And so the meandering of these jets, from a fluid mechanics point of view, are Rossby waves. Yeah. There are two jets on the Earth in general. Actually, on the southern hemisphere, you sometimes have two jets in the winter of the northern hemisphere. And so if we want to understand heat wave and extreme heat wave, it is about the nonlinear dynamics of these Rossby waves. And so what happens is that one of these meanders can become stationary in the reference frame. Here you have a meander, we have an anticyclone there. And so if it remains stationary in the reference frame of the planet for a very long time, or if this nonlinear wave breaks, then again you have a very stationary situation, and then this may lead to an extreme heat waves. So this is the extreme events that we want to study. So as you see, the qualitative nature of dynamics is not as difficult as you may have thought. I mean, the large-scale structure is rather simple, after all. It's nothing more than just a nonlinear waves on a structure which is rather coherent. So the numbers of active degrees of freedoms is maybe 20 or something like that. So it's not, and then you have, of course it is a turbulent flow, and we will model this with models which are tens of thousands or millions of degrees of freedoms, but most of the effect of the turbulence will be to act in a gentle way on this large-scale structure. So what people have done in order to study the probability and to look at the anthropogenic causes of the 2010 heat waves, so of course you go in the news and people ask you, is this event related to global warming? And so the scientific answer to this, which is a good one, is to do these kinds of curves. as you see here. So this is in the last IPCC report. So they run a model that have these kinds of dynamics, and they plot a return curve. So what is a return curve? So you define your extreme events. So here, for instance, you look at the temperature average during a month over Russia. And so 19 degrees is the average of your model. And 25 degrees was the 2010 heat waves over Russia. And so you ask, what is the return time of these rare events? And you make a plot where you have a return time here and the amplitude there. So as a function of the amplitude, you can read the return time. So you learn that the 25 degrees heat waves over Russia has a return time of about 30 years. And so what people want to know is these curves. And then you make two curves comparing two different climates. So the blue curve is for the climate during the period 2000-2009, and the green curve is for the climate during the period 1960-1969. And you will compare these two curves. And so you see that for the blue curves, you see that the events with 25 degrees has a return times which is 3 times less than for the green curves. So the return times of the heat waves has been decreased by a factor of 3 due to global warming. So in this sense, global warming acted on this event. So you can look at it the other way around. So you can fix the return time, 30 years, and look at the amplitude of the event. And then what you learn is that a 30 years event in the past climate was an event with an amplitude of 23 degrees, but a 30 years event in the current climate has an amplitude of 25 degrees. So basically this black arrow represents the natural variability of the system, the fluctuation you had without global warming. And this red arrow here represents the difference because of global warming. So then you can summarize it saying that the event itself is due to natural fluctuation. It is not due to global warming at all, but global warming increases it by this amount. And this amount is relative to the other, but still it has a huge impact. So that's the good way to do science about this. So it is these events are natural events, but they are affected by the climate change. So this is the point of my next slide. So the question, if you want to address it more abruptly, which is maybe simpler, is how good are the models to talk about these events? And so I will explain after how a model works. Okay, I will answer progressively to your question, but this is the basic question. Can we trust the models? Okay, can we trust the model to talk about these rare events? So on the qualitative levels, surely, but on a quantitative level, probably not. And we want to understand this better. And so we have to ask the basic question, is this internal variability well reproduced by the climate model? And so this may be even more challenging for extreme events. And so the main point is that in order to address this question, we need to understand well the dynamics and study the dynamical aspects of these extremes. So we really need to understand what is the dynamics that makes these events. And then once we have this, once we have properly sampled this, we can go back and ask whether our model was good enough to talk about these kinds of dynamics. So for now, I must say that we don't know, and this is the big issue. But in order to do that, in order to make this dynamical study, we need a good sample of events. And so we will need hundreds or thousands of realization of these events just to know what it is. And so this will be my point. I mean, my point today is just to talk about the sampling issue in this model. So, and basically, the point is how to study a 10,000-year heat wave with a 200 years computation. I mean, and that's why where I will use this rare event algorithm in order to answer this question. So the kind of model we have is this one. So first, here most of the dynamics is related to the turbulent dynamics of the atmosphere. And so we have an atmosphere which is described by a simplification of the Navier-Stokes equation. So it has something like 10 to the 5 degrees of freedom. And so this part, we can trust it extremely well because it's basically just Newton laws. The problem is that we cannot solve Newton laws at all scale. And then at some scale, we have to parameterize some of the processes that act on smaller scale. And so it's Newton laws plus effective parameterization of unresolved processes. And this is where the difficulty is. So among these unresolved processes, you have some relation with the sea ice, with the sea, so for instance the sea ice, with the ocean dynamics, with the vegetation, and with the terrestrial surface. So basically these models are the state of the art of what we can do in terms of using the Newton laws that we know and incorporating some long-term effect on non-Newtonian effect. So I must add that in the atmosphere, what is important for climate, is also the radiative balance. So there is a radiative code which is essential to the equilibrium of the model. And so this is how it looks like in this model. So the model we use is not one of the top class IPCC model. It would cost a lot. So we wanted to make a proof of concept. And so for this, we have used a model called Plasim from the University of Hamburg, which is a bit simpler than the one used by the IPCC, but which is the same as the one that were used before to study extreme in the IPCC report. So we want to show that it works in this model, and then to go to real IPCC class of model. So the dynamics look like this. So here you see again the 500 geopotential height, the line, the ISO line, and so you see the jet stream, and the colors represent the temperature anomaly, the difference between the average temperature in the model and the temperature at a given time. And so you see that, so this is Europe. We will be mainly interested for Europe as an example. So you see the jet stream, you see its meander, correlated with cyclones and anticyclones, and correlated with the temperature.
So in your model, of course, you count also for the season, the
No, in this proof of concept, there is no season. I mean, we are in what is called a perpetual summer situation. For simplicity, to be in a statistically stationary. But I mean, it's a technical point. No, the dynamic. You are right. The dynamic is completely deterministic. It is chaotic, also. It's clearly chaotic. But it doesn't change anything. Basically, it's just the same. Don't know why. So this is the climate of the model from the point of view of a jet stream. So here you see the mean kinetic energy in the higher troposphere, the jet stream. So you can look at the location of the jet stream. So this is what is called the storm track here. And so it gives you a climate which is reasonable compared to the real climate. We will not trust the model for quantitative result, but the qualitative aspects are correct. So I want to study an extreme event, so I need to define an observable. So the definition of the observable is a bit arbitrary. Well, it depends on which impact you want to study. So here we're studying extreme heat waves over Europe. So you see this is Europe, Western Europe, an area over which we will make spatial average.
You made Italy
Yes, well, that's how it is, unfortunately. So it shows you how bad is the model, actually, because you see this is a grid point. Yeah. Okay. So we will make spatial average, but we will also make temporal average. So here we will average over time, and this time average will be an average over a week or several weeks or 2 months or something like that. And so how long you should average is arbitrary. It really depends on the impact you want to study. So for instance, for the effects on human people, you want to average during several weeks because people first get tired and then they are not able to recover. And then finally it has an impact on their health. So for impacts on other things, you will have to choose other value of t. So this is how it looks like in the model. So this is just a control run. So here we have run the model 1,000 of years. And so the blue lines is the temperature, the daily temperature or the 6-hour temperature. And the dark blue line is the temperature here averaged during 45 days. And so you just have the time series. And so here you have one extreme. So we have zoomed in this extreme. And you see that during about 100 days, the temperature rises steadily and then goes down. And so you still have temperature fluctuation here on a time scale of a week. And this temperature fluctuation on time scale of a week are basically related to the passing of a cyclone and anticyclone, what are called synoptic fluctuation in meteorology. And so this is basically the correlation time of my systems, usually, in normal situation. So this time scale of a week is the times with which I will have to compare here this capital T, which is 45 days. So you see that here I have a time average of a time scale which is quite longer than the correlation time of my system. So this is where large deviation comes in. And so before going to large deviation, so let me explain you a few things that are probably obvious for this audience. So first, I mean, when you have a rare event, you want to compute a small probability. So here it's just the probability to be in the tail. The tail here is characterized by an ensemble A. So gamma A is the probability we want to compute. So if you just have an estimator based on picking randomly time or running your model long, then you will compute the relative error, and you will find that it is proportional to 1 over square root of gamma A multiplied by n. So there is the usual 1 over square root of n, but there is also gamma A, and gamma A is small. And so then if you want to have a good relative error, because your event is rare and gamma A is small, you will need to have n large, and n will have to be larger when gamma A will be smaller. So this is kind of trivial. So this is the point where you will need something else to sample your rare events. So one idea is to use importance sampling. So importance sampling is just if you want to, you have a PDF, a blue PDF here. So this is the tail of the distribution you want to sample. So let's assume that I am able to sample the green one rather than the blue one. And moreover, I know the relation between the green and the blue. The two are related through this function L here, that is called an importance ratio. If I have this property that I know the relation between both, then I can use the sampling from the green distribution to use this formula to invert my probability, and this gives me a new estimator for the probability to be in the tail here. And of course, because now the rare event became common, the variance of this estimator will be much smaller. It will be small. I mean, it will not suffer again the fact that the event was rare. So it seems kind of magic because, of course, the problem now is how to perform importance sampling for a climate model. I mean, is it... So this is basically the point. So the way we will do that, we'll use large deviation theory for time average observable. So as I told you, we will study time average of the surface average temperature over Europe. And so this time average will be over a time scale which will be rather long. And so I guess most of you know that when you study these kinds of probability, the probability that this time average is equal to A, then for large time you have this asymptotic result where it goes like exponential of minus t multiplied by the rate function I of A, where I of A is a Donsker-Varadhan types of rate function. And so it characterizes the rare events that corresponds to this time average, to this long time average. And so specifically for these problems, we use this we use the Jardina-Kourchan algorithm that allows you to actually make important sampling related to this long time large deviation theory. So what does this algorithm do? So P naught here is the statistics of your model. XT are all the variables of your model. P naught is just the PDF for all the statistics of your model. It is what you will get from your model just running it. P tilde of k is what the algorithm will give. So the algorithm will give P naught, but it will be tilted, and the tilt will be a multiplication by the exponential of k multiplied by the integral of 0 to t of something, an observable, of the system. So this sum here will, for me, will be the average temperature over Europe. And k here is just a parameter that the user choose. And so you see that the larger k, the more the PDF will be tilted toward large value of extreme temperature over Europe, average during a long time. And so for large but negative value of k, it is the other way around. And so this is just a normalization factor here for the two PDF, and lambda of k is nothing else but the Legendre transform of the large deviation rate function. So the Jardina-Kourchan algorithm was aimed at computing lambda of k. So we don't really care us about lambda of k, but still we will twist the algorithm to use it for doing other things. And so we don't want really to compute lambda of k, but it is a good way to make important sampling and in order to study extreme heat waves. This is what we will do. So the way it works, I mean, it is just like the 100 over rare event algorithm on the market. I mean, the idea is the basic idea is always the same, and then you have slight changes on the use depending on which kind of observable you are interested in. So it's basically an algorithm for which you will run an ensemble of trajectory, and based on this ensemble of trajectory, you will make diagnostics and select some of this trajectory in order to tilt the probability that you get. So I think the first example of such an algorithm was by Khan and Harris in 1953 at Los Alamos. They were studying neutron that goes through a wall, and the point were to compute the low probability that the neutron will actually go through the wall. And the event was rare, but the impact was important, so they had to study it. And so that's where they devised these kinds of algorithm. So the originality of this one is to use this kinds of idea to compute this large time, large deviation properties. So here we have n trajectory. At each time tau, it's about the correlation times of the model. Here it's about width, top. We make these diagnostics. So the diagnostic is to compute the increment of this quantity here. So the integral of the quantity between two of these times multiplied by k, we compute the exponential. W is just a normalization factor. So this gives us a number which will be the probability of this trajectory. So if this number is is 2.3, it means that we will randomly either make 2 copies or 3 copies of this trajectory, such that the average number of a copy will be 2.3. So basically, the trajectory that have large value of this quantity will be reproduced. Sometimes people call this cloning. And so when this number is small, the trajectory will be discarded. So the way it looks is you have your observable here, you have time, you stop, some of the trajectory are discarded, others are cloned, like this one. Here you have one more that is discarded, the red one, it has been cloned over the green one. And after some times, you reach a statistically stationary state for which the statistics of your trajectory has been tilted. And if the algorithm works well, which is not always the case, I mean something we have addressed here in a paper with Takehiro Nemoto made most part of the work. So when it works well, I mean it gives you a good sampling of the important sampling of the trajectory I was explaining before. So we have used that for our model. And so this is just a comparison of the estimates of the large deviation rate function, a comparison between the control run and what gives the model, just to test that the algorithm just does what it should do. So here we compute the direct estimate, the blue curve, is computing the large deviation rate function based directly on the time series, as was explained in a paper by Hugo recently. So we did exactly this procedure to compute it here. And then we compare it with what gives the rare event algorithm. So you see the black lines come from the control run with 280 years of computation. So the blue curves come from the control run with 1,000 years of computation. So you see that you can trust the direct computation for 2,080 years until about there. So it's the same for the blue curve. So we think that you can trust the blue curve until about there. And so you see that the rare event algorithm with only 280 years of computation is doing much better than the black curve. So you can, here you see the PDF of the control run and the rare event algorithm. So this is the PDF for time average temperature during 40 days. And you see that we have actually tilted the PDF as we wanted, and that the events with 2 degrees during 40 days became common in this, with this value. So this was obtained with k equal 50. And you can see here the numbers of extreme heat waves as a function of k. K, remember, is the control parameter of the algorithm. The more k is increased, the more you will study extreme heat waves. And so you see that for k equals 0, for the model, we have just 8 heat waves. And for k equals 50, we have several hundreds of heat waves. So the numbers of heat waves we will observe at a given numerical cost is increased by several orders of magnitude. Here, typically hundreds or thousands, depending on how extreme the events we study. So this is the point. I mean, at a fixed numerical cost, we get hundreds more heat waves with this large deviation algorithm than with the control. And so we can make a return time curve. So this is the anomaly in temperature for temperature average during 90 days. This is the return times. So the black curve is the control run. And the red curve is the one we got with the algorithm, with a cost which is 4 times less. So the cost of the black curves is about 1,000 years. And the cost of the red curves is 280 years. And so you can see we can reproduce the black curves, and we argue that we can go much further and talk about the return times of events that cannot be observed directly in the direct numerical simulation. So this is what we wanted to demonstrate. So now I will skip this movie. So how does the extreme event looks like qualitatively? So here what you see is statistics condition on the rare events. So we condition the statistics on the fact that the average temperature is larger than 2 degrees during 40 days. And then we get a map. And so the key point is that we have correlation between hot, extremely hot here and hot there and hot there. So you see that there are global correlation, something which are called teleconnection patterns. And so the fact that you have this global connection between value of extreme is related to the nature of the dynamics, the fact that we have these jets that has perturbation, which select some specific value of wave numbers for the perturbation. So I will skip this. So the conclusion for this part is that, well, this large deviation algorithm provides a wonderful tool to sample rare events, for instance, extreme heat waves. So we think it should open a new range of dynamical study in GCM and even the more complex one. So would you give me 2 minutes for showing 2 slides? So here we use a model, a turbulent model that reproduces Jupiter jets in a qualitative way, let's say. And this model produces several jets. Here you have 2 jets, you see the velocity. And we have first demonstrated that there is a control parameter for which you can have bistability switches from 2 to 3 jets. And so you can see here the switch from 2 to 3 jets that occurs on a time scale which is huge. So we have used another kind of rare event algorithm called adaptive multi-level splitting to study this transition. And basically, here again, what the problem is that we cannot study them directly. With this algorithm, we obtain thousands of transitions, and we have shown in a phase space, in an effective phase space, that this is the attractor with 2 jets, this is the attractor with 3 jets, and inside one of these blobs, you have 80% of the transition. And so this shows that the dynamics of the transition is concentrated inside these blobs. And so this is exactly the phenomenology of what is called an instanton. So here we get the instanton purely numerically using this kinds of rare event algorithm. And so we understand that the dynamics is predictable in this sense, that there are instantons. So there is a separatrix somewhere here. There is probably a saddle point somewhere there. And so this is the most probable path to go from one attractor to another. And so the model is non-equilibrium. So that's why the blue and red blobs are different. So one is for the forward transition and the other is for the backward transition. So we study this both completely numerically, but also we study it making the theory of these kinds of problems. So in terms of theory, I mean, if during the week, if you want, we have computed transition rate and a generalization of the Eyring-Kramers formula for non-gradient dynamics with Julien Régnier. And we also have studied large deviation for slow-fast systems with Eric van den Eyden, Tobias Grafke, and Thomas Tangarif. And we have an action that describes the large deviation for the Boltzmann equation, basically the macroscopic fluctuation theory for dilute gas. And so this is with Laure Saint-Raymond. So if you may be interested by this, so sorry for being late. So I will stop here. Thank you.
Questions?
Rob?
So for the rare event you showed with the climate dynamics, the temperature went up very smoothly and then went down very smoothly.
Yeah.
So if it was the Donsker-Varadhan regime, it should go up and then it should stay up, and then it should go down, I guess. So do you have an idea of how big time would have to be to see the real Donsker-Varadhan regime?
Yes, we have addressed this question. I mean, it will be a few months. I don't know if it's 3 or 4. So it is very long. And I mean, it is I mean, it is always like that in large deviation theory. So you have this very fancy asymptotic limits that are very nice properties. And I mean, they are very interesting to study, both from a mathematical point of view, but also they really give you an insight. But then once you are interested in application, you are nearly never in this asymptotic regime.
The cloning, you don't care. For the cloning still applies even if the time...
Right. That's the point, is that we are not exactly in the regime for the theorem to be valid, but still it tilts it in a way that it is useful to study events that are not in the asymptotic regime. That's the idea.
Juan?
So just in relation to what you said, and so you could try to reconstruct these distributions from short-time data using this idea of if you have enough statistics at short times, of high-order cumulants. I guess there was a talk by Kai
Bradhan, he is not here today, but yes.
Yeah. So there is information in the short time that then feeds into the long time.
Right.
Because properties in the analytic structure of the large deviation functions at long time are related to this cumulant. So I wondered if you have thought about that.
Well, that's basically what we do when we compute the large deviation rate function from the control run. From the statistics. So the point is that you need huge statistics, as you know. Here, that's the point. We don't have these huge statistics, and even using the model, it would cost so much to do that. But so that's why this algorithm is very useful, because it gives you an answer.
And the second part, you were showing this intermittency. You went quickly, but there was this time trace that jumped from 3 to 2.
Yeah. Jets. Atmosphere jet.
So that looks like, the kind of first order physics you also get in the intermittency in the dynamics of glasses and that kind of thing. So
right.
So there should be an non-analytic structure or traces of that in the large deviation, like the cumulant generation.
Right. Mm.
Have you seen any of this? That's how it should look.
Yes, you could. Right. So you exactly have this. I mean, it's a situation of first order phase transition with a bistability. So here, if you ask the question, why do you say it is a phase transition? Do you have something which becomes non-analytic somewhere? So we don't have something like the large numbers of particles, which is usually used in equilibrium statistical physics. So here, what we use as a parameter to define the transition is a timescale separation. So we have two typical timescale, and in the limit, when this timescale of separation grows, we actually get this non-analytic property.
I was just thinking whether you were doing large deviations on this problem, whether you had these cumulant generating functions as a function of the
right
conjugate field, and you saw the
change in shape. So here the large deviation framework is rather the small noise large deviation framework. It's the small noise large deviation framework. We do averaging, and when there is a timescale separation, the noise becomes small, and